Imagine injuring your elbow and not being able to play your favorite sport again or perform normal daily activities independently. Surely it's a horrible feeling. Treatments, therefore, for either severe injuries of the elbow or elbow arthritis can be in the form of total elbow replacements, where an artificial elbow implant replaces your natural elbow joints. Up until today's date, our understanding of the functional loading is still very primitive compared to other joints, such as hip, knee, or shoulder implants. Our current knowledge about the mechanics of the elbow joint dates back to models mostly generated several decades ago. Hence, there is no data to support implant design iterations, and most design evolutions have been based upon lessons learned from the clinical experience of failed implants. Now, with patients increasingly active, younger, and expecting to engage in sports, there is an urgent need to have reliable information about the force transmitted at the elbow during its functionality. Here is where my PhD comes in. For a first-in-human study, I am providing direct physiological data measured in real life for a number of reasons. One, for better understanding of the function of the elbow joints. Two, improve rehabilitation programs and activities of daily living for independence. Three, to optimize the redesign of elbow implants. I'm doing this by developing an instrumented elbow implant, which simply means design an implant with a cavity so I can house instrumentations and electronics inside to measure joint reaction forces. Such data are considered the gold standard by the orthopedic community, since they have the ability to validate current theoretical models and provide fundamental force data for understanding the function of the elbow. Now, since this has never been done before, I have spent the first year of my PhD designing and modifying an elbow implant in which I am embedding the electronics inside. So far, the design has been approved and the electronics are being attached to it. My implant design and functional capability is unique. There is no known competition. Therefore, making this project the first to generate real-time force and moment data during activities of daily living, which is eventually hoped to inform future implant design and clinical practice, specifically provide patient-specific treatment options and improving quality of life. It's worth mentioning that the far left X-ray picture you can see in this slide is my mum's broken arm. She has been suffering from severe pain for over 5 years since her little incident, and sadly, there was no treatment given for her specifically to improve pain over time. I'm hoping this research will provide a means for clinicians to facilitate more specific treatments for patients like my mum. Thank you.